Hello, I'm Roman, and welcome back to the series of the videos Neural Network from scratch in Go, where we using this book but implementing everything with the Golang. And in the previous video, I finally found the problem that I had with the implementation of the neural network. Turned out it was the problem with the what was this? Which one? Not this. Yeah. The problem was actually with the implementation of the relu activation backward method, and instead of returning the input based on the inputs, I had this condition like checking the input itself, and it led to incorrect calculation of the derivative for the relu activation function, and that broke everything. I mean, it's actually led to the thing that nothing was changed at all. So I had the same loss values, the same accuracy, and the model did not improve. So we fixed this, and then we're going further. Before we're going to do this, I would like to remind that I have a first channel, the first YouTube channel where I talk about different things in the around tech industry. I have some software engineering path videos or explain series, but recently I changed more on the talkative format. Hopefully you find it useful. But for now, let's continue to dive into the neural networks. So we're going to study the learning rate. And for example, with the learning rate that we have right now, which is equal to 1, I think. Yes, learning. Yes. So the stochastic gradient descent that we have has the learning rate equal to 1. So when we have the update parameter function, it takes the result of the weights and the biases, and it's just subtracted from the weights and the biases, and it might be a very big jump in the values. But so far we have a gradient of the model and the loss function with respect to all of the parameters, and we want to apply a fraction of this gradient to the parameters in order to descend the loss value. So right now we're just applying it as it is. In most cases, we won't apply the negative gradient as is, as the direction of the function's steepest descent will be continuously changing, and these values will usually be too big for meaningful model improvements to occur. Instead, we want to perform small steps, calculating the gradient, updating the parameters by a negative fraction of the gradient, and repeating this in a loop. Small steps ensure that we are following the direction of the steepest descent, but these steps can also be too small, causing learning stagnation. Yes, for example, we could reach, and I think we can see here, so the accuracy jumps between this value and this value for several times, and kind of going back and forth. So that might be related. Let's forget for a while that we are performing a gradient descent of an n-dimensional function or a loss function, where the n is the number of the parameters that the model contains, and assume that we have just one dimension to the loss function, a singular input. Our goal for the following images and the animation is to visualize some concepts and gain an intuition. Those will not use or present certain optimizer settings, and instead we will be considering things in a more general terms. That said, we have used a real HDD optimizer on the real function to prepare all of the following examples. Here's the function that we want to determine what input to it will result in the lowest possible output. So we have this function And we can see that the global minimum of this function, which is the lowest possible y value in this function, can output. This is the goal, to minimize the function's output to find the global minimum. So this is the global minimum. The values of x's are not important in this case. The goal is only to show the function and the learning rate concept. Also remember that this one-dimensional function example is being used merely to aid in visualization. It would be easy to solve this function with a simpler math. That's what is required to solve the much larger n-dimensional loss function for neural networks. Okay, so we have a function. We'll start descending from the left side of this graph with an example learning rate. So we kind of will start here, start in the first local minimum. So if we take the range from -3 to -2, this is the local minimum. But if we'll check the global minimum, it's right here, right? Yeah, it kind of jumps back and forth, and I think this is what I have in my example. You can see that the loss value and the accuracy kind of jumps around the same values back and forth, and probably because it's stuck in some local minimum, but we'll see. The learning rate turned out to be too small. Small data of this parameter caused stagnation in the model's learning. The model got stuck in the local minimum, but I think in my case it could be pretty big. The local minimum is the minimal is near where we look, but isn't necessarily global minimum, which is the absolute lowest value of the function. How do we know if we reach the global minimum or at least getting close? The loss function measures how far the model is with its prediction to the real target values. So as long as the loss value is not 0 or very close to 0, and the model stops learning, we're at some local minimum. And the closer loss value to the 0, the more correct the model in its predictions. In reality, we almost never approach a loss of the 0 for various reasons. One reason for this may be imperfect neural network hyperparameters. Another reason for this may be inefficient data. If you did reach a loss of 0 with the neural network, you should find it suspicious for reasons we'll get later in this book. Stuck in the second local minimum. So probably here it was increased. It's interesting, blinking and oh, okay. So I actually went far the first local minimum, but got stuck in the second one. Right? This time the model escaped the local minimum but got stuck in another one. Let's see one more example after another learning rate change. This time the model got stuck at a local minimum near the global minimum. The model was able to escape the deeper local minimums. I think it's referring to this one. So it might be counterintuitive why it's stuck here. Remember, the model follows the direction of steepest descent of the loss function, no matter how large or slight the descent is. For this reason, we'll introduce momentum and the other techniques to prevent such situation. Momentum in an optimizer adds to the gradient what in the physical world we could call inertia. For example, we can throw a ball uphill, and with a small enough hill or big enough applied force, the ball can roll over to the other side of the hill, like. Let's see how this might look like in the model training. "200 steps." Good. Yeah, really looks like a ball that was kind of rolling from this upper hill. Yeah, and the difference between dots, we can see that the kind of speed of the change is increasing. Okay. With the very small learning rate, here with a large momentum, the color change from green through orange to red represents the advancement of the gradient descent process. These steps. We can see that the model achieved the goal and found the global minimum, but this took many steps. Can we do better? Okay. Raise the global minimum, significantly better learning rate, so less steps. With this example, we were able to find the global minimum in about 200, 150 steps, respectively, but modifying the learning rate by modifying learning rate and the momentum. It's possible to significantly shorten the training time by adjusting the parameters of the optimizer. However, you have to be careful with these hyperparameter adjustments, as this won't necessarily always help the model. Unstable model, learning rate too big. If the learning rate sets too high, the model might not be able to find the global minimum at all. Even at some point, if it does, further adjustment could cause it to jump out of the minimum. We'll see this behavior later in this chapter. Try to take a closer look at the results and see if you can find it, as well as the other issues we have described from the different optimizers as we work through them. In this case, the model was jumping around some minimum, and what this might mean is that we should try to lower the learning rate, raise the momentum, or possibly apply the learning rate decay. I think this is too high. And it's gone. Oh. Okay. In this situation, the model starts jumping around and moves in what we might observe as a random direction. This is an example of overshooting with every step. The direction of the change is correct, but the amount of the gradient applied is too large. In an extreme situation, we could cause a gradient explosion. Broken model, learning rate critically too big. A gradient explosion is a situation where the parameter updates cause the function's output to rise instead of fall. With each step, the loss value and gradient, and I think, for example, this is the perfect example, right? We had, oh no, not for the loss. Yeah, these two. We had lower loss, and then we have a higher loss, and then again lower, but it's still higher than it was before. I'm not sure if it's explosion or explosion or the previous one, but still. At some point, by float point variable limitation causes an overflow, as it cannot hold values of the size anymore and the model is no longer able to train. It's crucial to recognize this situation. I'm not sure that's the case here. It's possible to tune the model's hyperparameter in time to save the model to continue training. When we choose the learning rate and other hyperparameters correctly, the learning process can be relatively quick. So the question is how we determine this hyperparameter, because we can set the very small learning rate and it will kind of learn for ages. or we can set a big one and we will never be able to train a model correctly. This time took significantly less time for the model to find a global minimum, but it can always be better. This time model needed just a few steps, like this one. It looks like some adjustable learning rate based on something. Because it's definitely not a constant, because I think, for example, here, where was the first example? For example, here, the learning rate was constant. It was the distance between dots is driven by the actual derivative change, but here it probably something else. The challenge is to choose the hyperparameters correctly, and it is not always an easy task. It's usually best to start with the optimizer defaults, perform a few steps, and observe the training process with tuning different things. It is not always possible to set meaningful results in a short enough period of time, and in this case, it's good to have the ability to update the optimizer's settings during the training. This is what I've been mentioning. How you choose the learning rate and other hyperparameters depends on the model, data, including the amount of data, the parameters, installation methods, etc. There is no single best way to set hyperparameters, but experience usually helps. As we mentioned, one of the challenges during the training of a neural network is to choose the right settings. The difference can be anything from a model not learning at all to learning very well. For a summary of the learning rates, if we plot the loss, very high, good learning rate. We can see various examples of relative learning rates and what loss will ideally look like as a graph over time. Knowing what the learning rate should be to get the most out of your training process isn't possible, but a good rule is that your initial training will benefit from a large learning rate to take initial step faster. If you start with steps that are too small, you might get stuck in a local minimum and be unable to leave it due to making it large enough. So starting from the small one is not a good idea too, as we can stuck in the local minimum. For example, what if you make learning rate 0.85 rather than 1? Let's try this one. 0.85. Well, it's not jumping above 1 value as it used to be, so it looks, but it kind of feels like the learning rate is still high in this case. By the way, do I have the not this main? Yes, I have the 64 nodes, not this one. Where is the SDG? Where is it? Optimizer. Okay, this one. Okay. Model training with SGD optimizer and lowered learning rates, but it's still ellipsing warning. Nice. As you can see, the neural network did slightly better in terms of the accuracy, and it achieved a lower loss, but by the way. Well, interesting, they don't have... Oh no, they have this... No, they don't have this jumping like I do, but probably based on the data, but still the accuracy... But the accuracy is actually jumping. right? Lower loss is not always associated with a higher accuracy. Remember, even if we desire the best accuracy out of our model, the optimizer's task is to decrease loss, not raise accuracy. I mean, this was always for me, like before I tried to study this, it was like lowering the loss is not always associated with the higher accuracy, but why then we don't optimize the accuracy? Why we're optimizing loss? For me, it was always the question, why do we need two metrics instead of one? But okay, loss is the mean value of all the sample losses, and some of them could drop significantly while others might rise just slightly, changing the prediction of them from a correct to an incorrect class at the same time. This would cause a lower mean loss in general, but also more incorrectly predicted samples, which will at the same time lower the accuracy. A likely reason for this model's lower accuracy is that it found another local minimum by chance. The distant path has changed due to smaller steps. Yeah, I think I have the same because, yeah. In a direct comparison of these two models in training, different learning rates did not show that the lower this learning rate value is the better. In most cases, we want to start with a large learning rate and decrease the learning rate over time stamps. A commonly used solution to keep initial updates larger and explore various learning rates during training is to implement a learning rate decay. The idea of learning rate decay is to start with a large learning rate, let's say 1 in our case, and then decreasing it during training. There are a few methods of doing this. One is to decrease the learning rate in response to the loss across the epochs. For example, if the loss begins to level out, plateau, or starts jumping over large deltas. You can either program this behavior, monitoring logically, or simply track your loss over time and manually decrease the learning rate when you. But okay. Another option which we'll implement is to program a decay rate, which steadily decays the learning rate per batch of epochs. Let's plan to decay per step. This can also be referred as 1 divided by t decaying or exponential decaying. Basically, we're going to update the learning rate each step by reciprocal of the step count fraction. This fraction is a new hyperparameter that we will add to the optimizer called the learning rate decay. How this decaying works is it takes the step and decays and the decaying ratio and multiplies them. Start learning rate multiplied by 1 divided by 1 plus learning rate decay multiplied by step. So it kind of so it decreases the learning rates based on the number of the steps. What is it? We then take its reciprocal further in training the lower the value and multiply the initial learning rate by it. The added one makes sure that the resultant algorithm never raises the learning rate. For example, for the first step, we might divide by 1 by the learning rate of this one, for example, which will result in a current learning rate of 1000. That's definitely not what we wanted. 1 divided by 1 plus fraction ensures that the result, the fraction of the start learning rate, will always be less or equal to 1, decreasing over time. That the desired result, start with the current learning rate and make it smaller with time. The code for determining the current learning degree is this. Okay. So for the first step, we have this learning rate. For the 20, we have this one. We can also simulate this in a loop, which is more comparable to how we'll apply the learning rate decay. So we have, for example, and it goes smaller and smaller. The learning rate decay scheme lowers the learning rate each step using the mentioned formula. Initially, the learning rate drops fast, but the changes in the learning rate lowers each step, letting the model sit as close as possible to the minimum. Okay, then it makes sense why we having the update params inside the optimizer, but not inside the layer, because we will be changing the learning rate. The model needs small updates near the end of the training to be able to get as close to this point as possible. We can now update our SGD optimizer class to allow for the learning rate decay. Pre-update params. I will read the description first and then I will code it, but then pre-update, post-update, okay. We updated a few things in SGD class. First, there is an init method that we added handling for the current learning rate. I have the function that is called new SGD, but maybe I will do the same with the initializer, like I have for all other things. Is now the initial learning rate. We also added attributes to track the decay rate and the number of the iterations that the optimizer had gone through. Next, we added a new method called pre-update param. This method, if we have a decay rates other than 0, we'll update current learning rates using the prior formula. The update params method remains unchanged, but we do have a new post update. Well, it's called the current. Let's use a decay rate of 1 fraction of 100 and train our model. Okay, so let's change it. Well, first this one, I guess it's called learning rate, and it will be current learning rate. Okay. Then I have the learning rate itself, which we will actually change here. Current learning rates, and we need some params. So the learning rate we have here, and that will be learn. We have the decay. Decay, which is plot again. Decay. And we have in iterations, and that's int. And we have iterations 0, right? I think I should not show the current learning rate outside. Okay, then I have all the factory methods, then I have func pre-update, and if it's actually, it takes the optimizer, right? And if the optimizer decay is greater than 0, then empty branch. It will not be empty very soon. So we calculating the current learning rate, and it takes the optimizer starting learning rate multiplied by 1 divided by 1 plus decay multiplied by optimizer iterations. Okay, and then we have optimizer post update iterations plus equal 1. So right now I should have errors here. What's the first? But I think I'm changing the second one, right? Okay, I'm testing this one, and here it will be again 1, and that should be the result. Oh, it prints the learning rates. Rates. And it's in optimizer. Oh, no, I need the current learning rates. Okay. Current. Our course pre-update and post. Well, the learning rate is decreasing. Accuracy is I would say not improving, or improving very... No, it's improving, but kind of slow. This model definitely got stuck, and the reason is almost certainly because the learning rate decay far too quickly and become too small, trapping the model in some local minimum. This is most likely why, rather than wiggling, our accuracy and loss stopped unchanging at all. We can instead try to decay a bit slower, but making our decay a smaller number. For example, this. Okay, let's try. Let's try. So let's... No. Well, the accuracy is much higher right now. In this case, we achieved our lowest loss and the highest accuracy so far, but it still should be possible to find parameters that will give us even better results. For example, you may suspect that the initial learning rate is too high. It can make for a great exercise to attempt to find a better setting. Feel free to try. Stochastic gradient descent with learning rate decay can do very well, but this is still a fairly basic optimization method that only follows a gradient without any additional logic that could be potentially help the model find the global minimum to the loss function. One option for improving the SDG optimizer is introduce momentum. Should I leave it for the next one? Probably it is, but I will try, for example, to start from this one, from smaller. So my current accuracy is 71% with the loss 0.69. Let's try again. Interesting. It became worse. Okay, let's get this one. And what if I will increase the number of the epochs? Will it make a difference? Yeah, so again we're kind of stuck. Okay, so it looks like this is our best result so far. But I'm curious if I will... Oh no, it's actually already found the local, because the accuracy is around the same and the loss for a very long time. So it looks like it found the proper value in around 9,000 epochs, and the rest is just jumping in between the same place. Okay, so the next thing is introduction of the momentum, and there is some code as usual, and we kind of going to, and then okay, there are next interesting things. I will stop for today. I'm not sure, maybe I will record another one today. We'll see. But yeah, I will stop for today. Thank you for watching, and I see you tomorrow. Bye bye.